This should be a pretty quick one because I didn't want to. I know I covered a lot in the last video, and I wanted to just kind of leave that be so you guys could work on the next problem once you were done. And so what I want to do is I want to cover, all right, how can I use MATLAB to calculate the derivative, the numerical derivatives using built-in functions? And realistically, there's not that many options, unfortunately. Really, there's these two major ones. Is that you can use diff, which calculates the forward difference of an array that you're given. And so to calculate the derivative using diff, you would have to do diff y over diff x. Because again, diff is just going to be the forward differencing equation of x. And so it also means that this derivative value will be one less because it can't use the endpoint. Because remember, the forward differencing method cannot use the endpoints. But it works. I mean, this will work. This will calculate dy dx. The other one is using the gradient function, which I mentioned in the last lecture, actually calculates the derivative using the same method that I was just showing you before. It uses the forward differencing method for the first point, the central differencing method for the center points, and the backward differencing method for the last point. And so that's kind of how that one functions. And so what I want to do is I'm just going to show you how to use these through example, as I try to do everything, right? And so what I want to do is I want to calculate the gradient I'm going to calculate the derivative using the gradient and the diff function. And I want to evaluate it from x is equal to 1 to x is equal to 5. And then I'm going to go through and plot the comparison of those values, the approximate value of the derivative to the actual derivative. And this is going to show you that these methods actually do work. They do something. They approximate it. Because like you can see in the final solution, and I'm going to walk you through all of it, the gradient function is actually really dang close if you use a small enough grid size. And that's kind of the control, is if you have enough points, you're going to get it pretty close because the error effectively travels throughout the length of the, as you kind of go through x, it'll get worse and worse usually. And we'll see that in differential equations as well. And so I'm going to show you how to do this, and I'm going to, it's actually very straightforward. And so let's just jump and dive right in. So what I want to do is I want to use the gradient function and the diff function to evaluate this. And so what I'm going to do is I'm going to create an x and a y variable. My x is going to go from 1 to 5, and I'm going to use 0.5. So my spacing is going to be 0.5. I don't remember what it was on my graph, but I can actually go change this, and then it'll change the solution too. And I can show you that. I probably will. It'll be kind of fun. And so y is this equation. It's going to be x to the 4th minus 3 times x squared plus 6. So I type in the equation. And now I'll just do, all right, I know what y prime is already, and so I'm going to type that in so I can compare it later on. Okay, so now I have x, y, and then I have y prime to compare with later. And so I'm going to do yp diff is going to be the derivative calculated with diff. And so remember, the way I do this is I do diff y not divided by diff x. And so that's the forward differencing of y divided by the forward differencing of x, meaning you just calculate the forward difference number y of y. So this literally diff calculates y of I plus 1 minus y of I. It just calculates one part of the forward differencing scheme. Okay, so that's pretty straightforward. And now the gradient, so yp gradient is actually going to be gradient of y comma x, because that's how you do the inputs. And so this is going to calculate using all of that work that I did in the example in the last video. This does all of that calculation for you. And so let's plot it. So plot, and I'm going to plot the actual data first, the actual answer. I'm going to do x, y, p, and I'm going to do red x's like I did before. I'm going to plot x, y, p, diff, and I'll use a black line. And then I'll do plot, I need to do a hold on statement, sorry. I'll do that in a second. X, then y, p, gradient. Oh, and I deleted my gradient equation. Gradient y comma x. And then I'll make that one be blue. So now I can see all of them pretty distinctly. And so let me do hold on here. I'm going to do my basic formatting of my plot. So fig1 is equal to figure. Should all be old news to you guys now. You all are pros at creating plots, hopefully, at this point. And now I'm just going to create a legend so that I can see. So actual diff and then gradient. So now I can compare these three answers. And let's run it and see what happens. Hopefully I didn't cause an error. I did. So to plot, they have to be the same length. Oh, I forgot. So remember, I even said it explicitly out loud that using diff, your answer is going to be one off, right? Because you can't use the endpoint. So length of y calculated with diff. I don't know what's going on. I think I just opened another one. Yp diff is going to be one different than length of x. See, so it's one less. I don't know why it just opened another MATLAB, but I'm closing it. And so now I need to do, all right, so I'm going to do, instead of plotting x versus y, so the reason I knew that is because my error in plot is vectors must be the same length. And so x is different length than y. So I'm going to do 1 to length of x minus 1. I'm going to include everything except for the last value. Oh, and I don't do that of yp, I do that of diff. I'm messing up all over the place, guys. I apologize. There we go, that's much better. All right, and so this shows you, all right, the red x's are the actual data. It shows me my gradient's actually still pretty close. My diff equation is way off, and as I told you before, the further you get away from the first point, the worse it's going to get. And you can kind of see that with gradient as well. And the reason it's not as close as what I showed you before is because, I don't know why I did a white background, but the reason it's not as close as before is because I used less points. So if I use, oh, I didn't set this equal to white, that's why. And so if I use more points, it should be more accurate. So if I change to 0.1, look, it got even more accurate. See, and so you can see, all right, now they're a lot closer during the whole length, and gradient is pretty much spot on for most of it. And the smaller I make this, the more they are on top of each other. There's still going to be a small difference at the very end, but as you can see, all three of these are on top of each other. So that's kind of the solution to solving differential equations even, is that if you can get a small enough step size, a small enough grid size, you actually get close and close to the answer. The problem is that it's more computationally intensive. And so when you do this, when we're going to do this with more complicated problems, that could mean changing the simulation from being like 5 seconds to 5 minutes. And if you're getting to something really, really complicated, like computational fluid dynamics is exactly like this. It uses similar methods to this that I'm showing you the basics of as like one of your intro classes. The smaller your grid size gets, it could mean it runs for days, weeks, months. Sometimes it'll take a month on a supercomputer, right? And so that's when these kind of concepts are important, because the smaller you can get, the more accurate, but it's always at a cost. There's always a cost to these things. But for what we're doing right now, you can be as brute force, use as small as you can probably use, as you want to use, within reason, and it will give you a very accurate answer. All right, and so I've shown you a couple ways that you can kind of solve derivatives on your own for class if you want to check your answers eventually. And so there's the solution. And so as normal, I want you to, for the next problem, go through and use diff and gradient this time to compute the derivative from these values, x is e to the negative first to e squared. So it's a little different now, right? So I want you to calculate that for y is equal to natural log of x and plot actual values. Y is equal to 1, y prime is equal to 1 over x. Compare that to your approximations using diff and gradient. All right, so next time I'm going to talk about the last topic, for the first week at least.